Hi everyone, my name is Arifah and I come from University of Surrey. Today I'm going to give a presentation regarding my research entitled Interpretation of Fast Field Cycling Nuclear Magnetic Resonance Experiment from Cement Materials. I'm going to start my presentation according to this order. First, I'm going to talk about the research objective, followed by the research overview, theory, methodology, results, and finally the conclusion. As for the objective, I'm using the molecular dynamic simulation to understand the dynamics of water in cementitious material to aid the interpretation of an MR experiment. And the first phase of my project has completed and it involved the MD simulation of aqueous ionic chloride. And this will be the focus of this presentation. Moving to the research overview, the relaxation rate response is dominated by the interaction of water with paramagnetic impurities. This would provide a new model called the Brownian shell model to describe the rotational motion of water in the vicinity of paramagnetic ion. This is an enhancement from the existing model known as Solomon, Bloomberg, and Morgan in 1950s. As for the theory, the water in ecosystem exists in two environments. First is the water that is bound to the first hydration shell or the inner sphere. Second is the remaining water that has dynamic characteristics similar to the bulk water. And there are 3 nanoscale time constants to describe the water and ion K dynamics. First is the tau x. This is the exchange lifetime of water molecules in the inner sphere. Second and third are the tau inner beta and tau outer beta. This is the rotation time of ion to water proton vector for the inner and outer sphere respectively. And to explain more about the new model, the Brown shell model is developed based on the Brownian rotational motion in aqueous ion complex. And as for the methods, I first conducted the MD simulation on aqueous sodium chloride, then I carry out the simulation on aqueous manganese chloride, and lastly the aqueous iron chloride. And this is the results of the probability density function describing the angle beta with time to validate the Brown shell model. It is found that the Brown shell model is fit to the MD at 10 picosecond using the tau alpha beta parameter. The best fit value for tau alpha beta is about 121 picosecond. And this is the result of the dispersion curve for aqueous manganese chloride. The red points are the experimental data and the solid line is the fit using the Brown shell model. The best fit value for tau inner beta is about 1 microsecond and the best fit value for tau alpha beta is about 127 picosecond. And this is the result for the radial density function on aqueous manganese chloride obtained from MD. And according to the radial density function, the agreement is impressive. Distance A that emerged from the fit almost coincide with the first hydration shell peak of the MD simulation. And the dashed line shows the distance D that emerged from the fit. Again, this sits in the region of the second hydration shell. And the last result is the dispersion curve for the iron chloride. The dotted black line is the model fit to the experimental iron chloride dispersion curve. And this is the curve that can be subtracted from the FFC and MR dispersion curve obtained from porous material in which iron is the dominant of paramagnetic impurities. As for the conclusion, molecular dynamic simulation confirm the validity of the Brown shell model and provide guide values for one rotational time constant. The key inner sphere time constant used in the fitting process is the shorter of tau inner beta and the inner sphere water exchange lifetime, tau x. The tau x is determined by the quantum chemical process and cannot be measured by the MD. And the Brown shell model not only improved the interpretation of relaxation rate result from cement-based material, but has broad applicability across the porous material sector. Thank you very much.